Welcome back. Let's talk about trees. We'll start off with some nomenclature. So here's a little tree. The little circles are called nodes, and the arrows pointing between circles are called edges, or sometimes they're called links. The first node at the top of the tree is called the root, and then trees that are at the bottom of the tree, or rather nodes that are at the bottom of the tree, nodes that don't have any arrows leaving them, are called leaves. So this is a leaf, this is a leaf, 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 leaf. A path along from the root to some leaf is called a branch. So here's a branch, here's another branch. We also use the term parents and children. So this node here, the root node, is the parent of these two children. And this node here is also a parent of these two children, and then this node is a parent of these two children. You can, sometimes we use the term generations, like this would be the first generation, has two children, second generation, two children, third generation, two children. Let's see, the height of the tree is the length of the longest branch, so it's the number of nodes in the longest branch. So the height of this tree is 4, because this branch is 1, 2, 3, 4 nodes long. All right, so that's the basic what things are called. So the next thing we can do is add properties that kind of determine the behavior of trees. So there's lots of different kinds of trees. For example, there's B trees, binary search trees, trinary trees, height balanced in trees, and many others. And we're going to look at some of these. So if we start adding semantic properties, we can reduce we can reduce the variety of trees, or that is to say, we can produce a specialized tree of some kind. So here's the first one we're going to add, this first semantic property. Let's just say that each parent has a maximum of 2 children. Let's just add that property. Then you end up with what's called a binary tree. So the binary term refers to the fact that there's a maximum of 2 children. So in this particular tree, this guy has 2 children. This guy only has one child. This parent only has 1 child. And then the leaves, of course, have no children. All right, so we can analyze that a little bit. What are the characteristics of a binary tree? And I've drawn a couple of binary trees here. Here's one that's fully filled, and it has a height of 2. And the number of nodes, n, is 3. So h, the height, is 2, and n, the number of nodes, is 3. Here's another one, just a couple random examples, basically. But this little guy here has a height of 3, and if he's fully filled, which he is, then he has n nodes in it, so n is 7. So in general, this was what that would look like, sort of plotting the height of a tree and the maximum number of nodes that you could have. So like this guy right here is here, he has 3 nodes, and ooh, this is wrong. This should be 7. Not sure what happened there, because I'm just using a formula in Excel. But anyway, that should be 7. 1, 2, 3, 4, 5, 6, 7. Yeah. 15 is good. And this is 25. That's odd that 1 there is off. Anyway, so generally speaking, we have this formula that relates the number of nodes in a tree to its height. And so the number of nodes, or the maximum number of nodes, is 2 to the h minus 1. So that's why this should be a 7, because 2 to the 3 is 8, minus 1 gives you 7. Not sure what happened there. Anyway, so this characteristic of binary trees leads to a couple of observations. One is that the inverse of 2 to the h is log n. So what that's saying is that to travel the height of a tree, we only need to travel log n steps, or we only need to look at log n nodes to go down the path. So that can be efficient if all you're trying to do is run down the longest branch. That particular operation, running down a longest branch, can be efficient for very large trees. Another way to think about it is consider a height of 64, just to pick a number. That's what I call a human sized number. Humans deal with things, and when numbers start getting too big, they start becoming hard to even comprehend, but this is a totally reasonable number, 64. But 2 to the 64 is this ridiculously large number. Right? This is what I mean by a kind of a non-human number, a number that's hard to even grasp. Like, how many is that? It's a lot, right? So for a reasonable size number, you get huge amounts of data. So what we're saying is that you could have a tree filled with this many items, which is a lot, and the length of the longest branch would only be 64. And that's 64 is a totally reasonable, easy to deal with number for a human, not to mention for a computer. A computer can do 64 operations in nothing, right? So a computer could run through a tree having this much data. It could run through the longest branch in 64 operations, which is nothing. So this kind of arrangement can be very efficient if you try and restrict your operations to just dealing with the height of the tree. All right, let's look at some implementations and the trade-offs that are associated with those implementations. So let's talk about memory storage first. So you could store a tree in an array. So here's a little tree, and here's the array that would store that tree. So I just have indexes 0 through 6. There's 7 elements in the tree. They have indexes 0 through 6. And I'm showing with the black lines here that, or with the heavy black lines, that each layer is stored between these black lines. So this is layer 1, the first layer where A is at, and then these two guys, B and C, are on the next layer indicated with these, between these two heavy lines, and then the fourth layer would be in here. So if we had another layer on here, it would have twice as many elements, right? Twice as many nodes. So it would have 8 nodes. So the next section here would be from 7 to what? To you got to count up 8, 7, 8, 9, 10, 11, 12, 13, 14, 15. Right? It would be from 7 to 15, or 8 more levels, or 8 more nodes in the next level. So there are pros and cons to this implementation here, this use of memory. And one feature, or you could call it a pro, I suppose, is that you can calculate, given the index of a node, you can calculate both of its children. You can calculate the index of both of its children, and you can calculate the index of its parent. So you can go up and down in the tree. You could imagine that this has arrows going in both directions, because we can go both directions in this tree with this little formula here. Try it for, like, let's see, node B, which has an index of 1. Its left child is going to have 2 times 1, which is 2 plus 1, an index of 3. So the left child is D. And likewise, we can calculate up. You could calculate A's index. I'll leave that to you to work through that. So you could consider this a pro, or an advantage of this memory organization. What about a disadvantage? Well, in order for this formula to work, you have to have these layers identified in the array, right? So let's say that some of these elements were missing. Like, let's say E, F, and G were missing. Then these spaces would be blank. And it gets worse. As the tree gets bigger, you're going to have bigger and bigger sections over here in the array that for each layer. So if you have a lot of empty space, this could be, there can be a lot of empty nodes in here. So you're kind of wasting space if the tree is not fully filled. All right, so generally speaking, in computer science, we have trade-offs. There's always a trade-offs between execution efficiency and memory usage, or between time and space. Okay, so this is one way to implement a tree using an array. Another thing you could do is a pointer implementation, which is probably more commonly talked about. But for pointer implementations, or also called linked implementations, use a self-referential data structure, this little node right here, and you have the keys, which are the letters we're talking about here. That's the key that identifies the node, and then you have pointers to the left and right. I think it's worthwhile pointing out that in a real tree there would be more information in here. I mean, what is the point of finding the key when you already know what the key that you're finding? There's no point in it. Just looking for keys is pointless. And what you really do is you use the key to find a node, and then in that node there's more information that you're actually interested in. So that there would, in a real life implementation, there would be more fields in here that would contain additional information that you're interested in. But anyway, we're just interested in, for right now, just in how these things work. So we just have a key, and then we have a pointer, a struct node pointer, so a pointer that can point to another node. We have a left pointer and a right pointer. So that's these little boxes here. So this little box contains an address. If this were C, it'd be a literal address pointing to another node, and this one points to that node, and this one points to that one. Okay, so there's pros and cons to this. What's a disadvantage of this? Well, look down here. These nodes don't point to anything, and there's 8 of those. So there's only 7 data elements in this node, but there's 8 unused pointers. So there's more unused pointers than there are data elements. So you're wasting half the pointers. That kind of happens all the time. Plus, on top of that, you just have to allocate room for the pointers. So up in the array implementation, all we had was data. But here we have to have the data element plus these 2 little boxes. So we're using a lot of data just for the elements that are in the structure here. There's that, and then half of the pointers are wasted. It gets even worse. Well, that's about it. But the advantage of this is that if the tree is sparsely filled, like if this whole branch were missing, well, then you don't have to allocate that memory, because we typically allocate this memory using dynamic memory, that is using the new operator. So we don't allocate nodes until we need them. Unlike an array, where in order to get an array to work, you have to allocate the entire thing before you can do anything, right? But here we can allocate nodes as we go, sort of make memory or request memory from the operating system, from the system, as we need it. So anyway, that's pros and cons in terms of memory. In a real-life implementation, you might do some data structure that has combinations of these things, and that's what they pay you for. At this level, we're just learning the basics of these guys and how they work in their most kind of classic form, but in real-life code is messy and has a little bit of everything going on. Okay, the first thing we might want to do to a tree is just visit every node and see what's in the tree. In other words, just traverse the tree and print out what's in there. Okay, we call that a tree traversal. So let's look at some tree traversals. There's a couple standard ways to do this, and it has to do with the order that you look at the nodes and their children. So we have a pre-order traversal, an in-order traversal, and a post-order traversal. And in the pre-order traversal, you're looking at the node itself, then the left subtree or the left child, and then the right subtree or the right child. And then in order, you look at the left, then the node you're pointing at right now, and then the right side of that. And then for the post order, you do the node last. So these 3 are the main kinds of the main order of doing these things. Now you could do the mirror image of that, and you'd end up with this. So there's 3 kinds: pre-order, in-order, post-order, and their mirrors, which kind of makes 6 kinds. It depends on if you count the mirror as a separate thing. which programmatically it's not. I mean, programmatically you're just gonna, it's the exact same algorithm with a less sign instead of a greater sign. So it's time complexity wise, these are the same, sort of, if you follow what I'm saying. Anyway, presented just for comparison, okay, is this messy algorithm here. This does a pre-order traversal, and it uses iteration and an explicit stack. So here's the iteration loop. Here's a stack operation, pushing. Here's a popping operation. So we have an explicit stack that we're pushing to and popping from. And then we have a loop, an iterator. And there's some logic in here, if else, a bunch of if else's, right? So it's kind of complicated. I would use the term messy. And I'm just presenting this in here because we can do better than this. That is, we can make a much cleaner algorithm if we can identify the recursive nature of these traversals. Okay, so if you think about traversal as a recursive kind of thing, which it is, then the algorithms become much neater. And really that's the advantage of using recursion, is that once you see the recursion, then the solution tends to be a lot cleaner. Okay, so I'm just presenting this as an example of how iteration with an explicit stack can be kind of messy compared to recursion. So the classic traversal algorithms are the recursive solutions. So let's spend a little bit more time on that. And okay, here they are. Let's go through this thing. So a recursive solution uses the built-in function call stack. So there still is a stack. It's just the stack is implicit. It's built into when you call a function. Okay, every time you call a function, it's using the stack that's built into the hardware and the language. Okay, the modern computers are sometimes referred to as stack machines because they have a stack, and the whole the system, the whole hardware and programming languages are set up to use this stack. Okay, so let's see, how are we gonna do this? And just dump the whole thing on there, I guess, and look at it all at once. So here's a pre-order traversal or an NLR traversal. Here's a in order or LNR. What did I say over here? NLR, sorry. And here's a post order. They're recursive. This guy is called traverse, and it calls itself twice. That's the recursion part. Same thing for this. This one's called traverse, and they're all the same. They only differ in where the processing happens. Here the processing happens first. That's why it's called NLR. Here the processing happens in the middle. Here the processing happens at the end. So by processing, we just mean, well, for us it's going to be printing. We just want to print the node. In real life, processing would be whatever it is you're trying to get done. Like you go in and find the key, and then you look up, an address or, a shoe size or something like that. That could be the processing. But for us, we're just going to print the key. Okay. So the thing to realize is that traversing a tree is a recursive thing. You can think of it this way. So we come in at node A, we'll print A, and then all we need to do is process A's subtree on the left. And then when we're done with that, we can process A's subtree on the right. And that's the problem. Then it breaks it into two subproblems. That is, we have to process the left subtree and we have to process the right subtree. Now, how do you want to do that? Well, let's just call traverse on that. Okay, so to process A's left subtree, which is an entire tree, just call the traverse function on B. Okay, that's the recursive idea. it relies on being able to see how a problem can be broken up into smaller versions of itself. Right? So processing the tree A breaks up into two smaller problems, and those problems are processing the left subtree and processing the right subtree, and that's seeing the recursion. So that's reflected in the code here. So this traverse algorithm, you call it on A, it's going to process A, and then it's going to process the left subtree and the right subtree. So we can kind of walk through this, and that's what this path is sort of trying to show here. And the output comes off in different orders, and I'm trying to show that with this little legend right here. The NLR is X's and the O's are, I keep saying that wrong. The X's are NLR, the O's are L and R, and the triangles are the other one. So let me try and walk through this and see if you can follow the words I'm going to say. So we want to process this tree. So we call the traverse function for node A. So we come into this function with a pointer that's pointing to the root node. The root node A is not null, so we print it. We print A, and that comes off here. Then we process the left subtree, so we pass a pointer to B. So we come back into this guy for node B. B is not null, so we print it. Then we pass a pointer to D. So we come back into another instance of traverse with D as the root. It's not null, so we print it. That's this thing, D coming off. Then we process D's left subtree, which is null, which means we come in here with a null, a 0. It's null, so we return. That means we were going to return back to where we left off, which was when we called this function here for D's left subtree. Then we do the same for D's right subtree, which is also null, and we'll come in at 0 and then come right back. Then we're going to return back to where we left off from, which was when we called traverse for B's left subtree. So we're going to come back in here, right? We're going to come back after the call for this, like right between these two guys, you know. Then we'll call traverse for B's right subtree, which is E, like that. So, you know, you should walk through that yourself and kind of think it through, and I'll show you another way to diagram this in a minute, but the net effect of all of this can be represented with this line around the outside. The only difference between these three functions is when the processing happens. So if you follow this path and you do the processing immediately, then you'll get this sequence here: A, B, D, E. As we go along the path, as soon as we come by a node, we process it. And then if you do the processing in the middle, it means you're going to come along this path, and you won't do any processing until you come back from D's left subtree. So D will come off here with a circle. And then you'll come back from processing B's left subtree. That's when you'll process B. So the circle comes off here. Then you'll do B's right subtree. You'll do E's left subtree. You'll come back. You'll do G's left subtree and come back from that. Then you'll do G. Then you come back and you do E. You come down here. You go left. Come back. Do H, like that. Likewise, the diamonds indicate when the processing would occur for the nodes if you did it, last. So the processing for D comes off after you've done D's left subtree, which is null, and D's right subtree, which is null. Okay. Now, you should kind of go through that exercise yourself slowly and try and hold as much of it in your head as you can. It's hard to imagine because once you get so deep in here, you can get a little bit lost. So you might want to do this. So here I've done a hand execution method for the recursive calls, showing all of the boxes for the functions. And note right away that the recursive call execution itself is a tree. It sort of mimics the structure of the tree that we're trying to traverse. Right? It'll have the same shape exactly, missing nodes and all. So let's go through this on this tiny little tree just a little bit. So here I got this tree with A, B, and C, and I'm going to do a pre-order traversal. So I'll do the process first, and then I'll do the left subtree and the right subtree. This is what the tree looks like with a little at a little lower level of abstraction. Right? Like here I'm just showing nodes, but if you show the nodes and their pointers, it looks like this. So I've got a root pointer, which is a global data element, outside of any functions, and it points to the root. Just a pointer. And this guy is a node, which has the data element and 2 pointers in it. And the left pointer has the address of B, that is, it points to this node. And the right pointer has the address of C, points to this node. And then the left and right pointers are null. Also indicated with a ground symbol. Null is just 0. It's just a fancy way for computer people to say 0. Like when you're given a phone number, you could say O instead of 0 to sound, like that's what everybody does. I don't know why. But if you're a coder, you could give your phone number and list O's, and then you're really signaling to your coder buddies how cool and nerdy you are. Because nerdy is the new cool, I think. At least I like to think so. Anyway, just being silly there a little bit for a minute. So let's see. So we come in here and we go through this path like we did before, and you can do that and think and try and understand it that way, and that's good. Or you could draw this diagram here, right, and show what's happening. So let's see. We got main, where we call traverse. That results in a box for the traverse function, and the address of A is passed into this node or root variable. Then the first thing you do is process A, so the output comes off A. Then you call traverse B and pass the left pointer, which is the address of B. So that's the argument that's passed into this box. So we got another instance of traverse, right, taking up memory resources on the stack, right, on the call stack. That's where this guy lives. So there is a stack involved here. Anyway, call B, which results in another instance of traverse taking up a room on the stack. The root is null, so this guy returns right away back to here. Then we call this guy, and B's right subtree. We just did the left and the right subtree on B here. And we come back, and likewise, and then we come all the way down here, and then we go over here. Okay, so this is a good method as an exercise for really helping to understand recursion and trees and even addresses at a very low level. One thing I'll say is this depth right here, this is the height of the tree. Okay, so we're going onto the stack one level, then we're going another level onto the stack, then we go one level deep onto the stack, and then we come back, and then one level deep again on the stack, and come back, and come back, then we go deep again. So what's the deepest we're going to go on the stack here? What's the height of the tree? And remember back when I was looking at 64, what if the height of the tree were 64? Then the tree would be gigantically enormous. So what I'm saying is we're not going to go very high on the stack. We might go 32, 42, something, not that high. So we won't fill up the stack if the stack is a reasonable size. We won't fill up the call stack in the language and in the system for this particular algorithm. Okay, so you shouldn't get a stack overflow here because you're not going that deep on the stack. But keep that in mind, because we might later on, we might see an algorithm where we do go very deep on the stack, and you'd get a stack overflow, but not on this guy, because we're only going the height of the tree, which isn't much for a binary tree. Okay. So let's shift gears, or let's add a little more to this. So far we're talking about binary trees. Right? They're binary in that there's two children. And that's the only semantic property that we've added to the general idea of a tree. We've just, taken the general notion of a tree and said, what if we restrict it to two children? Then, we have this log n and a lot of stuff going on, log base 2 n. What would happen if we add another semantic property? So let's add another semantic property where we say that the data, the values in the tree have a certain relation. Okay, so we're going to say, let's add the semantic property to a binary tree that the left child is smaller than its parent and the right child is larger than its parent. So like for humans, you could do this with your kids. You have kids and they're all different sizes. Some kids are tall, some kids are short, and you might have a kid that grows up to be taller than you. So you'd put him on the right if you got a big old giant kid. And then if you have a short kid, you put him on the left. So you can do this in real life. That's a way to organize your family. So you can find your kids a little bit easier just by looking at their heights. You don't have to remember their names and stuff. So this is where the efficiency of traveling the height comes into play. Because if you do this with your children, you only need to travel the height of the tree to find any particular child. Okay, so this semantic property combined with the binariness of semantic property gives you what's called a binary search tree, and this is where we can really utilize the efficiency of a binary tree. And we'll talk about that a little bit more. So let's talk about insertions and deletions in a binary tree. So here's the algorithm for doing an insertion. You make a new node, clean it up, put the data in it. If it's the first node, you just hook it up to the root and leave, you're done. Otherwise, you got to do these two steps. You got to first find the insertion location. So you need to traverse a particular branch, looking for an empty spot, basically, and then you need to hook up the new node at that spot. So the shape of the tree, let's go ahead and do that for a particular sequence, and the sequence that you're given will determine the shape of the tree. So you could think of this as the order that data arrives, like the order that, say, your customers arrive in a store. You have no control over when your customers walk in the door. You just need to stick them in a tree. So let me rebuild this tree and I'll show you the process. So 5 shows up. That's a new node. So you just put him in there and you're done. Okay, then 4 shows up. So you always start at the root, and then 4 is less than 5. So that kid is smaller. So you put him over here. Then 7 shows up. You start at the root. 7 is bigger, so you go over here and you put him on the left. Then 2 shows up. You start at the root, smaller, you put him here. 9 shows up, bigger than 5, bigger than 7, you put him here. 8 shows up, bigger than 5, bigger than 7, smaller than 9, you put him here. Then 6 shows up. It's bigger than 5, smaller than 7, so you put him here. 1 shows up. Smaller. 3 shows up, smaller than 5, smaller than 4, but bigger than 2, so he goes here. Okay, so the resulting shape of the tree depends on the order. It's not fully filled, right? There's a whole branch missing from this guy, and there's a branch missing from this guy. So it's a little bit sparse. So once again, back to the memory representations. If we were storing this in an array, we're missing 2 elements on this level. We're missing, there's a maximum of 8 elements on this level, and we're only using 3. Right, so we'd be wasting 5 elements in the array on this element, on this, if we were using a array to store this in. Okay, but if we were using a linked memory representation, we might come out ahead. I think you have to count it up, but we'd only be allocating memory where we have nodes. But each of those nodes has pointers, and you know, it might be better than an array for this particular tree, but you'd have to work it out. All right, so here's another tree that's even worse in terms of the balance, in terms of what we call that balancing. This guy is fairly balanced, but could be worse. This guy's even worse in terms of the balancing. This is wasting a lot of space. Okay, what's the worst space that you could do? Well, if I had the sequence, if I had this, that's the way my orders or my customers showed up. You know, like say they'd have to plan that. You know, they'd have to hang out outside the store and sort each other like they do in the military before they start marching around. You know, they sort each other by height, so it looks pretty. But if they did that, I mean, they walked in the door that way, then the resulting tree would look like this. Okay, so the height is equal to n. So we're losing the log n, right? We're losing the log n advantage of a binary tree here. So what we're saying is that the log base 2 sort of height, the log base 2 height assumes a fully filled tree, or really a balanced tree. So we're going to look at that next. We want to try and keep the tree balanced. That's going to be the next topic that we're going to cover. Okay, so that was how to do insertions, the tree that you get. Let's talk about deletions a little bit. So here's the rules for deletions. You first need to find the node that you're going to delete, and then you have 2 choices: either delete the so you delete a node, which we'll call the parent, and you replace the parent with either the smallest node on the right. So you look down the entire right branch and find the smallest node, or you could search the entire left branch and find the largest node and replace the parent with that. So we have two ways to do that. So on this guy right, let me show this. On this guy right here, if we wanted to delete 2, then that's going to show up in one, the resulting tree would be one of these. So we want to delete 2. So I could replace that with the what is it? The smallest node on the right. Smallest node on the right is 1. So wait a minute. Yeah, so I misspoke, right? So if we want to delete 2, we could find the smallest node on the right. I have to look at the instructions here. The smallest node on the right. So the right, this is the right, all of these nodes. The smallest one is the 3, right? Yeah, the smallest node on the entire right branch is the 3. So you could replace the 2 with the 3. That's one way to do it. And the other way you could do it is replace the 2 with the largest node on the left. So there's only one choice, it'd be the 1. And so you could replace the 2 with the 1 here. Either way works, and the resulting trees maintain the correct semantic property. That is, for every node, the left child is smaller than the parent and the right child is bigger than the parent. That's true for every node. It's true for 9 here. This guy's smaller. It's true for 3, smaller, bigger. It's true for 7, smaller, bigger. It's true for 4, bigger. It's true for 5, bigger. Let's check here. Smaller on the left. Okay, for 1, we check. Bigger on the right. For 7, smaller on the left and bigger on the right. Check. 4, smaller on the left, bigger on the right. Yep. 5, bigger on the right. Everything's cool. All right. That's binary. That's what did we do? We did trees. We restricted them to being binary. We talked about the log n-ness of that. Then we looked at restricting the order of the child nodes to bigger and less than, and that results in a binary search tree, which has the advantage of when you're doing a search, you never have to travel more than the length of the longest branch. That's a binary search tree because, you know, if you're looking for 3, for example, I'm going to start here, and I know 3 is less, so I'll go this way. It's less, I'll go this way. It's bigger, I'll go that way. So I found it, and I only had to travel the height of the tree. So that's takes advantage of the fact that the height of the tree is log base 2n, the number of nodes. Okay, so binary search trees are super efficient. All right, that pretty much wraps this up. Hope that was helpful to you all. See you next time.